So let's get started. Um, so another nice day out there, and so hi to all of you who chose not to be in the classroom this nice day today. Today we're starting the last section on class on uh, so for doing data mining on data represented as graphs. Um, um, and we more or less had one lecture on this earlier on spectral clustering, where we looked at representing data as graphs and then how to do clustering on the vertices. And this converted the graph into an eigen problem on like a matrix. And so one of the ways I approach data mining on graphs, and we teach mostly in this course, is trying to convert graphs into large-scale linear algebra problems. We'll see a different way of doing that today through Markov chains. So before we get started in the lecture, let's look at the schedule where we are. There are 4 lectures left in the semester, and then things are going to get crowded. I hope to have, there's one more homework out on graphs that's not due until, I put it on the day after the last day of the semester. If you want to do earlier, we can have it. I guess we had a vote. If you want to do earlier, we won't have it due earlier. I'll try and have this out pretty soon, like so hopefully before class on Wednesday. And then you should be able to get started on it. It'll cover most of stuff in today's and Wednesday's lecture. So that should be out soon. Okay, what else do we have coming up? The final report is due in like a little over a week. So that seems the final reports due a bit earlier in this course than other course, so you can work really hard on this one and then do yours for the other classes. It should be up to 4 pages per student in your group. So if you have 3 people, up to 12 pages. If you have 2 people, it's only going to be 8 pages. It does not have to be that large, but most people typically write a report in that range. You can put more stuff in the appendix. I will read through all of the reports. That is 100-some students at 4 pages per student. So only put in there what actually needs to be in there. Figures and stuff is great. It helps me read through the reports and get the stuff pretty, absorb the information more quickly. So it's coming up soon, but I know that I saw a lot of great progress at the intermediate report. So I know a lot of almost all the groups are in great shape for that. And then you'll have to do a poster. The poster will serve as your final, right? I put it in the slot when we're supposed to have the final. So I don't want you to do the poster. The poster should be about the completed project. So it's not due until after you've turned in your final report. Because we have a late exam slot, it's not as crowded as it is some semesters. If this is an early exam slot, it's even more hectic at the end of the semester. But the poster outlines will be due on the Monday of the end term test. Which is the last official kind of day of this class for this semester. I'll bring a bunch of sample posters back in for you to look at again and get some ideas as you're finishing up your project. There's going to be bonus points awarded. Everyone will get to vote on their favorite posters. You'll get a chance to go around and see everyone's other posters. It's going to be a lot of fun. We will print the posters for you. There's a $15 fee for the class that goes towards printing the poster. so you'll get to vote on other people's posters, and so you will be able to, the winners of this will get some additional bonus points towards their group. All right, so we're looking for creativity, good visual displays, capturing a lot of information, and interesting projects. Great. So that's coming up. Any questions on wrapping up the project and what's left into that? As you get really close to the deadline, I'll review again the specific criteria I'll be looking for. Again, I'll be looking for fairly specific things when I'm grading. I'll read through them all, but I'll be looking for you hit kind of certain points of evaluation. So if you hit those, you're going to do fine on the project. Okay. And then the last thing will be the end term test. This will be like the midterm test. It will be in here on the last day of the classroom part of the semester. It will cover, I think I will cover starting with the streaming algorithms, because felt like those people didn't do so well on them on the midterm. So I kind of pulled most of those questions off. Well, I'll probably ask about that, then into dimensionality reduction, noise, and the graph analysis. All right, so that's what it will cover. It will be kind of like the midterm. We'll see. Probably that midterm was a bit too detailed, and I had to do some corrections afterwards. Hope not to have to do that this time. All right. Any big picture questions on these as we get going? Yep.
Will there be a practice test for that?
I don't have a practice test. We'll see. Hope maybe I can get something together. But I think I don't have one ready. If I do, it'll probably be made up of old questions that I don't like. Okay, so there'll probably be questions that I think don't do, that they were like problematic in some way, right? So I don't want to ask that version of the question again. So, but it'll give you a sense of what will be covered. But I'm hoping you've got a pretty good sense of, I don't know if it'd be great to calibrate how well you know the knowledge, because I probably won't use kind of the best questions I have. But I hopefully get a sense from the actual midterm and from doing the homeworks, what should be on it and how to study. Okay, but I'll see if I can get something together. It won't be a lot ahead of time. I want to make the actual interim test yet, and I just kind of crafted the last assignment, and we're finalizing that. Next project for me is to get the interim test ready. All right. So and then if I hopefully then I can put together a practice one. But so maybe in the week before I'll get something out. Yeah, so okay, great. So we'll start the graph sections again. We've kind of already touched on graphs when we were talking about clustering, where we talked about how to convert and kind of a similarity function or a similarity graph that was ones that things were similar, zero if they weren't, into kind of using the eigenvalues of the normalized Laplacian matrix to convert it into a kind of a Euclidean representation where we could then find clusters either by just looking at one dimension and splitting them, or into low dimensions and kind of visually circling them or running k-means clustering. Markov chains is going to be another area that is effectively going to take graph data or something like graph data and convert it into a way where we can apply the tools of linear algebra to do some analysis on it. And so we'll be mostly abstract today, looking at graphs, and then the next lecture on Wednesday, we'll see kind of a very famous example of how this was used. So how many people have seen Markov chains in a class before? Okay, and how many people have not seen them much before? Okay, great. So I'm hoping that usually when you're talking about Markov chains, you're presented a view. There are two different ways of thinking about Markov chains and using them, and I will try and talk about both. Most classes will only say, here's one view that's convenient to me, and they'll only talk about that way. And there are kind of these two different views which are similar. They're both ways of converting Markov chains into using essentially the linear algebra structure, or kind of modeling it as kind of a random walk on a graph, and using the outcome of that in order to model something. But we'll think of two different ways of kind of working with this. So it's also kind of getting late in the semester. A bunch of you are looking for jobs, and I know that's especially stressful this year. The economy's probably not helping. Last episode of A White Lotus, I'm thinking more like philosophical. Okay, so I'll try and bring some life lessons to kind of this, I kind of give some levity to the lecture a little bit. Okay, so you know, here are life lessons you can learn from modeling things as a Markov chain. Your current position matters going forward. Don't worry about the past. Okay, you only need to worry about one step at a time. You will get there eventually, or possibly you won't. And in the limit, everyone has perfect karma. All right, all seem maybe reasonable, maybe not. We will see each of these throughout the lecture today, as in these are all personified by a Markov chain. Okay, so look for these throughout the lecture. Okay, so again, we're modeling graphs, and I'm going to give my, I guess, favorite example of a graph that we've seen earlier in the semester with spectral clustering as, okay, we can often see this as just a drawing with eight nodes, A, B, C, D, E, F, G, H, right? And then there are edges between them, right? The red lines are the edges between them. That means those nodes are connected. You can either represent this kind of just mathematically write out a graph as a set of vertices and edges, right? And so you have the vertices with the labels, and the edges are just the unordered pairs between them, okay? And in this lecture, at some point, we'll talk about ordered pairs a little bit more, but these somewhat matter in the modeling. I think sometimes it matters if you model the ordering, and sometimes in the big picture, it turns out not to make too big of a difference. But for the modeling in this lecture, we will want to pay attention to the ordering of these edges, right? So that would mean that AB would be, if it was A to B, that would be a directed edge from A to B. It means if you're at A, you can only walk to B, but you can't necessarily go back from B to A. Okay, that's what this representation says. And so we'll change that a little bit. But what we saw before was unordered. Before we'll look at some ordered representations. Okay, again, another way of representing the graph is think of it as this table, this adjacency table, where I have a pair of entries, right? And I want to consider the edge between E and F, right? This edge between E and F, well, I look at E and F in the table, and I look here, and there's a 1. Okay, and lo and behold, it's unordered. So if I look at F and E in the table, I get also an edge here. Okay, so it's not ordered, so it appears in both of these spots. It's kind of duplicate information. Okay, and I can represent this table of 1s and 0s as a matrix, adjacency matrix. You write a matrix, again, the structure matters, so you put the rounded parentheses around, okay? With the matrix representation, you can then apply some linear algebra on the problem, and we will get to this eventually. Okay. Okay. All right. So a Markov chain, okay, is then something that takes in, it's going to look very similar to a graph representation, and we'll basically look at converting a graph into this. But involves 3 components to formally define a Markov chain. Okay, so first you have to have the vertices, and that is these kind of vertices here, the list of vertices, same as with the graph representation. Okay. Second, you have the probability transition matrix. Okay, and so this is pretty closely associated with the edges. And what I did, I started with the adjacency matrix, and I did a fairly simple transformation of this. Okay, so I took all of the, let's see, all of the edges of A, C, and I can go from A to B, C, and D, and that means I had ones in these locations before, and I convert them into 1/3, okay? And what I've done is I've taken this column and I've L1 normalized it. All the values were greater or equal than 0, so I have to, if they were negative, I wouldn't necessarily know how to do this, but I took this column, let's call this, if I say that this column here this is the adjacency matrix, this overall is A, and this is A sub A, or often like A1, okay? This column here now is A1, which is a vector, divided by A1 norm, but the L1 norm. Okay, what is the L1 norm? This is going to be the sum over j equals 1 to, let's say, n, okay, of AI or A1j absolute value. Okay, remember those absolute value to the first power, then taken to the power 1/1, right? This was an LP norm. This is A1 norm. Highlight that here. This is the 1 norm. So implicitly, I'm taking this to the 1th power, and then I took this whole thing to the 1 divided by 1. Okay, but all the green stuff isn't doing anything with the L1, right? So I'm taking to the first power, dividing, and then taking again the whole thing to the 1/1, which is the, no, not the 1/1, it's to the, yeah, it should be the 1 over, yeah, that's 1. Sorry, I was worried that was 0 for some reason. Okay, the 1/1 power, which is again 1. So this whole green part doesn't do anything. Okay, this is the L1 normalizing. What does that mean? What is the resulting? How can I think of this vector after L1 normalizing? What special property does this have? Assuming that they all started as positive, or non-negative values. Yeah. Columns will sum up to 1, but how can I think about columns that are positive and everything sums up to 1? What's nice about that? Its hint is in the name. What's the name of the matrix?
It's each of the values is the probability that the edge is going to be or something like that.
Yeah, we'll get to the effect on the edges, but it's probability, right? So I could think of this as a probability. Okay, so I have this entry, I'll call this equal to P1, right? P1 will be in this space of probabilities, and it's a probability vector. Okay, so P1j is going to be something like the probability of something having to do with j. Okay, so I'll think of it as a probability. I know that some of the things are probability 0, and the other things, they all have a value between 0 and 1, and they have to add up to 1, right? This is the kind of the definition of a probability over a finite state space. I can represent it this way. Okay, so what I've done is I've converted every column now into a probability vector. Okay, so this is part of the input. I've taken the graph, and if I have a kind of an adjacency matrix, I L1 normalize the columns, and I get into a probability transition matrix, is what will be called. Every column now is some sort of probability associated with an edge, right? Or with the vertex, right? So this is now, so P1 equals P of A. This is P1 equals P of A, which is the first column here. This is some probability of being associated with A. Okay, what's it going to be? We'll see this a bit more. But if I'm at A, I'm going to move to one. If I randomly walking on this graph, I'm going to move to one of the adjacent nodes, and whichever one I pick is going to be at random. Okay, so this is the standard way of converting undirected graph into a probability transition matrix. Okay. All right, and then there's one final element here, Q, which is called the initial state. And so this is not part of the graph input, right? The V and the P part, those I can read directly off the graph. This initial state Q, sometimes I will call this Q0. This is going to be an initial state. Okay, and okay, I like if the input is just a graph. So I would like not to have to specify this initial state. Okay, what is this initial state? I'm going to pretend I'm doing a random walk around the graph. The node set tells me where I can walk to. The probability transition matrix will tell me something about how I can walk around, and we'll play with this a little bit in the next few slides. The initial state says, where do I start the random walk? How do I start the process? Okay, and I'd rather not have to specify that. Okay, so the first half of this kind of lecture will be about how do I not have to specify this initial state. I don't want to specify. It doesn't, if I choose a different initial state and it ends up with different answers, then it's not telling me something inherent about the graph in some way. I wanted to understand the graph or some form of this input in some way. And so if I have to specify that, then it's like, okay, well, it's kind of not as useful. All right, it's still useful in various ways, but it's kind of I'd like to get rid of this aspect. Okay, so these are the three parts that define a Markov chain. Okay. Okay, so let's, and so an example of an initial state would be, there are two examples. One, and these are kind of, so the first one says, I'm starting in location, the second index, which is B, right? So I'm starting exactly in this location, right? This is one representation. This one is kind of in some way a structurally different representation, where I'm saying I'm going to start with a probability distribution over my initial location. Okay, so I'm going to start with a probability distribution over my initial location. I don't know exactly where I'm starting. Seems a little bit more odd. And then I'm going to do a random walk with only a guess of where I actually am. Okay, so let's start with just this first one. It's a little bit easier to conceptualize, and then the second version, which will be, we'll see we can use that as well. And again, the goal is to kind of get rid of this initial state. And then tomorrow we'll go back, or Wednesday we'll go back and think, okay, when do we actually want to think about specifying something more about the initial state in various ways? So the idea of this, again, is we're modeling a random walk on this graph. And so we're thinking of starting in this initial state here. We're starting on location B, right? And now our goal is to kind of understand if we did a random walk from B. So if we started here from state B, well, then we can look at this column, the B column of the probability transition matrix associated with state B, and that tells us where we would possibly go, right? So that says we're initially in this state here, okay? And then we want to this is equal to Q. And then we would like to apply the probability transition matrix and says, where would we likely go afterwards? And the output of that is, so the initial state is this Q vector, and we would like to apply the probability transition matrix. So we start here as the input, and then we output one of these two locations, and these are equally likely, right? So so this is not the orange one, right? Okay, so now the blue state is here. So I can represent where my distribution of where I would be after one state as after applying the probability transition matrix. I have two possible edges. I take each with equally likely probability, and I can view this now as a state Q1, right? So now I have a distribution after one step. I'm in a position Q1. Half the time I'm in state A, right? This is half the time I'm in state D. Okay? And you can imagine, again, this matrix here. I was in B, and I could only go that orange dot. I can only go to A or D. Is the two options here, right? And that checks out. Yeah. Well, in this probability transition matrix, it says no. Okay, but it is okay to do that. It is okay to model this as staying in this location. What would that mean? That's a great question, right? So if I look at this entry here, this is 0, and the way I wrote this down, the whole diagonal is all zeros, right? But if I had some of the probability of staying in that state, well, then this would just be non-zero. So I could put a non-zero step here. One way of modeling this that may or may not have certain advantages is you kind of assign a fixed probability to stay in your exact location over time. That would be a reasonable way of modeling this. And doing like the Laplacian and working with the Laplacian, which we saw for spectral clustering instead of the adjacency matrix, is kind of doing something like that. It puts one there and negatives in where the adjacency is. It's kind of a different philosophy, but it's kind of allowing you to have some probability of staying in the same state. And this would be a perfectly reasonable different way of modeling this transition from the graph into this, but this is the most simplest standard way of doing it. Okay. Yeah, that's a great question. Yeah, so okay. So this was after one step here. Okay, what if we take another step in the random walk? Well, how is that captured? Right? I had this nice thing before where I could do one step. This is one step. Okay, if I want to take another step, 2 steps in the random walk, right? Well, then what I need to do is I can take the output Q1, and now I apply this probability transition matrix again. Remember, I was half the time, so Q1, I was 1/2 here, and I was 1/2 here, and then I have to distribute this probability here and this probability here. Well, I can write this as linear algebra to get a state Q2. Okay, so I can do this to get a new state Q2 after 2 steps. Okay, and the output looks like 1/6 the time I'm going to be in state A. I got that from 1/3 times 1/2. So 1/2 probability of being in the state, and 1/3 of the time I went to step A. Okay, but if I look for the second state, I wound up in B. Well, now I have to get this by 1/2 the time I was in state D, and I took a step here, right? So this would give me this would give me 1/6 again, but I could also get it by being in state A and taking a step in order to get to B, right? So I have 2 ways of getting there. So I get 2/6 instead. And the same for being in state C, and then 1/6 again for being in state D. Okay. And I know I cannot get to states E, F, G, and H with only 2 steps. The probability of being in those is 0. Okay. Okay, and then I can repeat this again, right? I have state Q2 here. I map it. Oh, yeah. So it'll also be useful, before I do this, it'll also be useful to think of this as taking mine from my initial state and multiplying by the matrix P twice. And because it's a square matrix, I can do P squared. I can actually if I wanted to, I could pre-compute P times P and get P squared, right? What does that mean? I'm multiplying the matrix by itself. I can, with linear algebra operations, I can change the order I perform the multiplication, right? It doesn't matter what order I perform the multiplication, the result will be the same, at least in a pure mathematical sense. Numerically and from an algorithmic perspective, it may matter which order I do them, but from a mathematical perspective, I could actually pre-process P squared and say, well, Q times the P squared matrix, I immediately know where I would be after 2 steps. I just apply that once. Okay. And so then I can keep doing this random walk, right? Now Q2 is mapped down again, and this is actually Q. Remember, this is equal to P cubed times my initial state, right? And this will get a different distribution matrix. All right. And now a little bit of the probability has leaked out into state E, right? So I've moved this a little bit further. So I take my distribution of where the state's going to be, and I multiply it by the matrix. So I can think of putting kind of Q2 transpose as being kind of along here. And I have a probability, and I push it down each of the columns. And what comes out the right-hand side, right, is going to be Q3, right? So I push the probability down the columns, I multiply it by the values, and it pushes out the left-hand side. That gives me states Q3, right? So if you remember how multiplication of a matrix by a vector works, you can think of it procedurally exactly like how the probability transition matrix works. Right. Yes. Okay. Yeah. So what's going to happen? So the big question, I guess, is what's going to happen if I keep doing this, right? So what if I keep doing this over and over and over again? Okay, what would happen is we want to understand this limit. Let's say one way of writing it is Qn, right, is the state after n steps, right? Where I have, or I can think of multiplying this matrix by p to the nth power, and then I do times q. Right? Or alternatively, this is P times P right? So this is n times. Okay? So I'm gonna kind of do this as in the limit as n goes to infinity. What's going yeah. So so what's gonna happen? What do you think is gonna happen?
Balance out.
So it's going to balance out, right? So is this going to be so uniform? Is Qn going to equal to 1 over like the number of nodes? Is this what it's going to look like in the limit as I keep running this? Seems reasonable. You keep walking around, you could wind up anywhere, right? So if you're walking on a kind of a big checkerboard, in a bounded space, you could wind up anywhere after long enough. Who's to know? Okay, so who thinks? Does everyone think it's going to wind up uniform or something else? As uniform? Okay, who thinks something else? Okay, what else do you think it's going to be? What would other options be? If it wasn't uniform, then what's it going to be?
I mean, if there's.
Okay, if there's cycles in a graph, let's say the graph was a big cycle, all I can do is walk in a circle, and maybe I can't get outside the room. Someone locked the door, I'm a robot walking around, and there's a door that locked, I can't get out of the room, I'm only in kind of some limited part of the graph. So it might not be uniform then. But if I'm walking around in a circle, would it be then uniform on the circle? It might be uniform on a circle, maybe. So it thinks it'd be uniform on a circle if I constrained it. If that was, then that's the answer. Okay. Everyone's satisfied? Okay. So the big kind of point of Markov chains is it is not uniform. Okay. The limiting distribution is really interesting, and it's not uniform even over a constrained space. Okay, and so something about the limiting distribution tells you something fundamental about the graph that we want to study. Okay, it's not uniform. Some areas will be higher traffic than other areas. Okay, if I have a room and I'm walking around randomly, right? It's harder to get to the middle of the room up there, right? I'm more likely to walk through the hallways or something like that. If I get stuck in a corner, well, it's hard to get over to the corner. I'm less likely to wind up over here. And if I get over here, I'm going to walk out of the corner. There's only one way I can go. So I'm less likely to wind up in the corner. I'm more likely somehow to be in the middle of the room where there's lots of ways to move around. Because maybe it's a little bit unintuitive, but the idea is the corner over there is kind of an isolated part of the graph of the space. And so I'm less likely to be over there, where somewhere central, has a lot of connections, I'm more likely to be in that location. And that tells me something interesting about the graph. Okay, so this is very much not uniform. And how it's not uniform tells us something interesting. Okay. Okay, and so this, okay. This is this first life lesson. Only your current position matters going forward. Don't worry about the past. Okay, so let me mention this is called a Markov chain, because this is modeling where the probability transition of a random walk on the graph only depends on your current state. Okay, and so we're thinking about that, and this is enough to model this graph. I can model the graph by only looking at the node and walking to its neighbor at random without and that's enough to give me this complex information. Okay. Okay. So at this point, I want to. There are two ways of moving forward about thinking about this Markov chain. Okay. So there are two ways of kind of thinking of a Markov chain. Okay, so the first way is to only consider one possible state, this would be a node, at a time. Okay, so this would be e.g. that my Q0 or kind of Qi in general was 0, 0, 1, 0, 0, 0, right? So it looks something like this, where I had a single one, right? I have a single state, one possible state, and the rest are 0. So I'm thinking about actually walking on the graph, and I'm actually always in exactly one position at a time. Okay, and so that's consistent with what we talked about before. And okay, and there are some, and in fact, we'll talk about some algorithms for understanding this. And there are some algorithms that actually work by considering one position at a time, right? This is intuitively, I can only be in one place at a time. Okay. The other way is thinking about a probability kind of distribution on the states. Okay, and so this was kind of this example where kind of Q0 was the starting point was 1/3, kind of 0, 0, say 1, 6, 0, 1/2, 0, right? So it's still added up to, everything's still added up to 1, but now my estimation of where I am, right now my estimation is spread out non-uniformly potentially over multiple possible states. I'm in a quantum state of 3 different locations at once, or all the different locations at once. Okay, and so when we were modeling this, where are we going to be after 3 steps? We eventually got this probability vector that had 5 possible locations and a probability distribution over that. We're maintaining all possible worlds at the same time. Okay, whereas the first one, I'm only maintaining 1 possible world at the same time. The one I'm currently in, I'm in a simulation of the world, and that simulation is only maintaining 1 single state at a time. And so these are 2 different views of a Markov chain, and they correspond with different algorithms and different uses, and they're both very useful. Okay, and so often you might think of, if you're in a kind of a class about finite automata, right, where you're thinking about a state machine, you're probably in the first case. You're thinking about a state machine, your execution of a program. I'm in exactly 1 state, and there's a state graph where I can go to. I can't be in multiple states. Okay. The second one is what you think about often in Bayesian data analysis, right? Where I'm thinking about, I want a distribution over the states. I want to explore the different probabilities of where I could be. I want to model this probabilistically. Now, how you might implement it might be like the first one, okay, where you actually do random walks on the state space. But how we were talking about maintaining with the linear algebra, you get these different states, the quantum states of being everywhere at once, kind of simultaneously. Okay, but there are other parts in data analysis, especially understanding graphs, where maintaining this becomes too much information, and instead I want to do a bunch of actual short random walks, and sometimes that works a little bit better. We're actually randomly walk something on the graph to see how well it works. Okay, and so we'll kind of go back and forth between these 2 ways of thinking, but kind of be aware, if you're reading this, they probably will give you one of the 2 perspectives. Either you're physically doing a random walk on the graph and you're keeping track of where you are, and I'm keeping counts of how many times I land in a state, or I'm keeping this distribution by applying this linear algebra, pushing this forward. Okay, if I have a discrete state space, I can do this. If I have a continuous state space, right, that's maybe not models a graph, then I kind of need to do the first one, because I can't necessarily maintain a continuous distribution as easily. Okay. Okay, there's one more before we get into analyzing, right? Remember I mentioned this limiting state, and this Qn equals or as n goes to infinity in the limit, right? So I have to talk about as Qn as n goes to infinity, and in the limit, remember Qn is equal to p to the power n, right? For some initial state Q0. Okay, in order to talk about this, I told you this was going to be very interesting. But the problem is I have to talk about a limit. Let me write this. Important. Let me write it a little bit more carefully. Okay, a limit, and I need to make sure, right? If you've done some kind of, you've taken number of, more advanced math classes. When I talk about taking something to the limit, I have to worry that the limit actually exists. Okay, so the limit of every process does not always exist. And so I can't always talk about the limit of something. Okay, the limit might be something that's infinite, or it might not converge, and there are lots of weird things that can happen. Okay, so what I want to talk about is an ergodic Markov chain, which is a special type of Markov chain where the limit exists. Okay, so this is when the limit exists. Okay, and the definition is a little bit technical. Okay, so an MC is ergodic if there exists a T, which is the number of steps. Okay, there exists a T so that for all n greater or equal than T, then Q of n j is greater or equal than 0. Okay, so that the probability of being in for all, this is for all j in this indexing to the nodes. Okay, so it's ergodic if kind of eventually, if I run it past the time t, then from that point forward, every possible state has a non-zero probability, has a greater probability of being true. Okay, so I want to understand when is a Markov chain going to be ergodic, and this is just by reading this definition, you should probably not understand when it's going to be true. And I want to be able to take my graph and be assured that I can understand that the limit exists for me to analyze it. Okay, so it turns out there are 3 conditions that I have to pay attention to. And instead of saying when it is true, you can say when it's not true. Okay, so not ergodic if and only if there are 3 conditions I have to worry about. Okay, so the first one is has kind of these absorbing, and I'll define all these, and transient states. Okay, the second one is that it's disconnected. Okay, and being disconnected, we talked about already. If I was a robot walking around the room and the door's closed, I couldn't open the door, I can't get outside, right? So if it's crossing that one out, but if it's disconnected, and then the third one is if it's cyclic. Okay, so the cyclic means that I can walk in cycles in a very special way. Okay, and if I can do this, then it also, there's the limits not defined. All right, so let's kind of now, and if none of these 3 conditions hold, I know it's ergodic, I know the limits defined, and I know that I can, and then we'll talk about how to calculate it. And then I can calculate the limit, and it will tell me something very interesting. If these do not hold, then maybe I can't calculate something interesting. Maybe it's still somewhat interesting, but not as interesting as if the limit was defined. Okay, so these are the 3 things I have to check for. All right, what are absorbing and transient states? And I'm going to basically explain these all by example. That's all kind of technical to write down the actual characteristics, but here are 3 different examples, and all I need to write down is the probability transition matrix, okay, to understand if this is true. Okay, so the probability transition matrix, let's draw these graphs. Oh, and I should mention that we started by converting an undirected graph into a probability transition matrix, but I don't need that to be true. The probability transition matrix, all it needs to be true is that it needs every column to be L1 normalized. Okay, as long as that's true for every column, it's a probability transition matrix. That's what the definition is. So I don't need it to come from an undirected graph. Okay, it could come, but that it always means I can represent it as a probability state transition where I have a probability space. So this first one has two states, right? And the first one goes 1/2 probability to the other one and 1/2 as a self loop, right? So your question, can we go back to the same state? In this case, I can, because I've got this loop here is exactly this guy, right? And what does the other column says? Well, that means if I'm in the second state, state B, I go back to itself with probability 1. All right, so what happens here? Well, if I start in state, let's call the first state A and the state B, right? This is A and B. Okay, if I start in state A, half the time I go to state B. If I go to state B, I get stuck there. Right, so if I'm starting in state A, kind of, well, what's happening? I always have some chance of staying in state A, but in the limit, it's what's going to happen to the probability of being in state A in the limit now. After one step, the probability of being there is going to be 1/2. After 2 steps, it's going to be 1/2 times 1/2, a quarter. And after that, 1/8, right? So after n steps, the probability of being in state A after to the power n is going to be 1/2 to the power n, assuming I started in state A. If I started in state B, I'm always staying exactly in state B. My probability always stays there exactly. Okay, so here I don't kind of in the limit, I'm not getting, all my mass is going to state B. Okay, so this is kind of, I'm not getting anything in the limit in state A, and this is kind of weird. Okay, with 2 states, this kind of tells me something useful, the limiting distribution, but we'll see some weird things that can happen as I get to kind of larger states here. Okay, so this second example, let's say I have A, B, and C. Okay, A was A doing. A is always going to B. Okay, this seems reasonable. B is always going to A. That seems reasonable. Okay, and I have a state C. C is always going to B. Okay, with probability 1. Okay, so if I start in state A, well, then I cycle between states A and B. But if I start in state C, I transition A and B, and I never come back to C. Okay, so I'm doing something maybe interesting between A and B, and I can learn about that, but I've lost information to learn about C. Okay, and then let's look at this third example here. Now I've got A, B, C, D, E, and F. Okay, I have, let's see, I have A and B. And these basically have 1/2 staying where I am and 1/2 going back to itself. So B back to A is 1/2, and B to itself is 49 out of 100, so slightly less than 1/2. And then I also have C, D, E, and F. And once I get in here, I have all these edges. It's like I had this undirected graph. I also have this self loops. But there's some very small probability that B leaks out to C, 1 out of 100. Okay, so if I start walking around in states A and B, well, I'm going to keep most of the probability in A and B, but slowly it's going to leak out. And then once I get into states C, D, E, and F, then there's something, ends up going to be uniform in here because the transitions are uniform. And it will slowly gain all of the probability is going to be in this part of the graph. Okay. What that means is that once it's leaked out, I've lost my information about how A and B interact with each other. So you can imagine that there was actually something very more complex happening between A and B and maybe more parts of the graph there. But eventually all my probability leaks out. And so in the limit, I don't gather any of that information. All the information is leaked out of A and B. So I can't really say useful about the whole graph because I have this property. Okay, so what are absorbing and transient states? Okay, so these are the absorbing states. Okay, and B is going to be absorbing state, and the transient states are the ones where I could be leaking out of these, right? These states are going to be the transient states where I'm leaking out of this information, right? So I'm eventually wind up in these absorbing states that gather all information, and I've lost information to the transient. Okay, so if I have this situation, then in the limit, I don't really capture information about the whole graph, only about the absorbing states. Okay, there can be weirder things that can happen too. I should have put this on the slide, but let's say I have A here, and I have, let's say there's a self loop 1/2 the time, and 1/3 the time it goes to B. And then B goes back to itself, and C happens here. And let's say C has a self loop. It could be more complicated. And 1/6 the time it goes to C. Well, now I either go to B or C, or maybe a whole subgraph in these two regions. And depending on initial guess of where I went to B or C or where I started, I never know information about the other absorbing states. So I may not even know information about all of the absorbing states, depending on some early decisions in the process or my initial states. So that's why when you have these absorbing and transient states, this is not going to work. I kind of need to be able to get from any node to any other node. If I can get from any node to any other node, then I do not have absorbing and transient states. So no absorbing plus transient if can get from any node to any other node. Okay, so if I can get from any one to any other, I don't have this problem. Okay, have a more extreme example of that would be these unconnected examples, right? This would be A and B here, where A is a self loop, B is a self loop. This could be A, or this would be A, B, and C. Well, now A can get to B and B can get to A, but C can only get to itself. Okay, and then, yeah, so how many connected components does the third example have? Let's see, I have A and B. These can get to each other and stay to themselves. C, D, and E. These can somehow, C can get to itself, or D, or E. E can get to each other and to itself, and D has no self loops, but get to C and D. And then I have another state F that can only get to itself. So I have three different components here, disconnected components. Again, depending on my initial condition, that tells me how the probability is spread out, and I can't ever change that in between these states. Okay, so this also is not ergodic. Okay. Okay, and then the third example say this is the most confusing. This is where cyclic examples don't have a limiting state either. Okay, let's go through the first example here. And this is where I have a probability if I'm in A, I always go to B. And if I'm in B, I always go to A. Okay, so let's say now that my initial state is I'm starting always in A. And so after one step, what's going to happen after one step? One step is going to be P times Q0. It's going to be 0, 1. I'm always in B. Okay, so what is going to be, so I need, in order to be ergodic, I need after T steps, I always have some chance in being in each of the states, right? So what if I'm in Q17? What's Q17 going to look like? It's going to look like 0, 1. Every odd number state, I'm going to be in location B. And every even number state, I'm going to be in location A. But that depended on my starting my initial condition. Okay, so it'd be dependent on the initial condition, and so I have a 0 probability of being in one of the states afterwards. So this also means it's not really limiting; it's oscillating between these two states. Okay, cycles don't have to be of length 3. I can also be A, B, and C, where these transition. I get that the right way. A goes to C, C goes to B, and B goes to A, right? So that if I start in state A, then every number that is a multiple of 3, I'll be exactly in state A, but I won't be in the other states. Okay, so again, it's not limiting because it's got this very regular structure, which is oscillating. Okay, I can also have this where, let's see, what did I draw in this example? Yikes. Okay, A is here, and I'm also going to put F over here. Okay, and this is B, C, D, and E. Okay, what is happening here? A goes equally likely to each of these 3 states. And same with F. F went this way. Okay, and going back the other direction, everything only went from this side to that side. Right? So I'm basically getting a bipartite graph. Right? The graph kind of has this bipartite structure where if I start in A, then every state 0 and every even number state will be in A or F. If I start in B, C, D, or E, then if I start in A, then every odd number state will be in B, C, D, or E. So it alternates between these two clusters, or these two subsets of this bipartite graph. I have no edges between A and F, and no edges in between B, C, D, and E. Right. So if I get this sort of structure, then this is a directed bipartite graph. I also have this cyclic structure. Okay. If I were to take this and add a single edge from E to C, that happens 0.001, right? Is this still going to be cyclic? It's no longer going to be cyclic. This is now fine because now I could come over from A to E I'm in here with, say, probability 1, I'm in one of these 4 states, but some probability stayed in the right-hand side on the even number steps, right? There's a very small probability, but once that's there, it'll eventually spread completely over here, and it only has to be one direction. Now I can switch up the even and odds. Okay, so adding 1 makes it no longer cyclic. This breaks the cyclic structure. Okay, so you can get this cyclic structure. Most commonly, you get it of this type here. This is the most common. Okay, you get a a piece of the graph or a little graph that's alternating just between two states, right? But as soon as you have something of cycle 3 and something of cycle 2 in the same graph, well then, and they can move between each other, well then it's not cyclic. The whole graph has to be cyclic for it to be a problem. Okay, so these cyclic things can happen and they're weird, but you can't have them to be kind of, if it's going to be ergodic, and then you don't have a well-defined limit. Okay. Okay, so let's see. Okay, so now I can say if the Markov chain is ergodic, okay, now I can think of P star as, what if I take Pn, P to the n, as n goes to infinity? That's saying I took an infinite number of steps, then I took in any state, I applied P star, the P star matrix, right? And I'm going to get a state Q star. Okay, so if it is going to be ergodic, okay, if it's going to be ergodic, then it does not matter. So it's not going to matter. So then the initial state Q0 does not matter. For any state I start in, I'm going to get the same Q star in the limit if I did this an infinite number of times. Okay, and so this is what I like. Then if I have a graph that I set up the Markov chain so it's ergodic, then it doesn't matter what the initial state is. Then I'm just talking about the graph structure, right? And that's what I want to do. I want to analyze the graph structure with this limiting state. Okay. Okay, so this is what I would like to do. And okay, we have another life lesson. You just need to worry one step at a time. You'll either so eventually get there, or you won't if has kind of absorbing and transient states. Then well, maybe not, right? So this is maybe not. If it has absorbing and transient states, you may not actually get somewhere. But if you are ergodic, okay, then you will eventually get there and limit just one step at a time. Okay, great, good. Okay, so this limiting state has a lot of nice properties. One of those is called the delicate balance. Okay, what is this saying? It's saying that it has this property that if I'm in if I'm right down my state, my Q star state, so limiting kind of state, and this, remember, this state Q star is in this probability distribution over the nodes, right? So I have a probability distribution of where it would be on a random walk on the graph, defined in a certain way, okay? Well, that means that if I look at the probability, this is equal to the probability in state I, okay? Theory. Okay. No. Gosh, need to. Okay. All right. Probably I'm in state I, and this is probability of moving to state J, given that in state I, right? So say this is the probability I'm in state I. This is the probability that I'm moving to state J, given that I'm in state I. That's what the probability transition matrix is telling me, right? That's the ith column and the jth row. So given I'm moving through this column, the probability I move to state J, that's reading that off is. So if I'm in this kind of converge to limiting state, then this is equal to the inverse here, right? This is, and the right-hand side is the inverse. This is the probability I'm in state J, and then the probability of moving to state I, given that I'm in state J, right? So that there's this J and I, these two states. Then in the delicate balance, that the probability moving between them is balanced. I'm not changing the probability between them on one step. Okay, that's what this is saying. So I'm saying if I move by one step, I'm in this state, P star times Q, this is equal to Q star. Okay, so if I'm in state Q star, and then I apply the probability transition matrix, I get back to state Q star. Okay, so that every part of it is stable, is delicately balanced. Okay. Okay, now we're going to look at this term here. What does this tell us? Oh, okay, so before we do it, okay, in the limit, everyone has perfect karma, right? So in the limit, as you walk around randomly, eventually you give what you get. Okay, so let's now, so let's look at the state Q star here. What does this look like in this example graph, right? Was this going to be uniform? Okay, again, this is lesson, this is not uniform. Okay, not uniform. The probability, where are the probability higher? Let's look at these nodes. At 3, these are higher for nodes A, C, D, E, and F. Okay, it's kind of medium for B and G, and it's lowest for H. Okay, so the fact that you had 3 things that are exactly the same is a little bit, it's not unusual. It's unusual as you get to bigger graphs, it gets more spread out. But what you want to take away from here is node H, right, is kind of isolated. It's kind of in the second half of the right half of the graph, which is not as well coupled, and it's kind of a tail off the end of there. So this one is more isolated than the rest of it. So it's a lower probability of being there, right? When I wandered over there and got stuck in the corner, well, I found my way out of the corner, and I haven't wandered back over there since. Okay, so if I wandered over the corner too many times during the lecture, you would get worried, right? So it makes sense that I'm standing here, right? And then B and G are a little bit more isolated than the other ones, right? So the ones more in the center that you can get to from lots of other positions seem more likely to be kind of to have one of these higher values. Particular F is kind of interesting, right? This is F is right here. This one basically gets all of, anytime you're in H, the next state you're always in F, right? So it gets everything from H, it always absorbs all of its mass, or it could get it from G or E, right? So it happens to match the degree of the node in some way, but that's not always going to be true. Okay, and the point is it's not uniform. Okay, it's telling you something automatically about this graph. Where are the interesting things? Okay. Okay, so I want to go back and look at this equation right here, which we kind of derived by saying, let's say we took P star to the limit, and we took at Q star, and we multiplied it by P one step, and we got back to Q star. What's going on here? What is What's happening here? What's interesting about this particular equation? Yep.
Isn't that basically saying that, you know, with this, limiting state Q star, you know, even if we take a step, we're just going to go back to where we were?
Yeah. Okay. Well, what do you know from linear algebra when you see this equation? That's right. Yeah, that's correct. But what do we know? What does this equation say within linear algebra? Yeah. It's the identity. Identity. What's identity in German? The eigenvector. Yes. Yes. It's the eigenvector. Great. So the identity, it's not say the identity matrix, but you're getting back your own matrix. It's the self vector, which is the eigenvector. A little German lesson. So this is the Q star is an eigenvector of P. Okay. So it's an eigenvector of P, the probability transition matrix. Okay, when I have this property where I multiply a vector times a matrix, I get back the vector. That's a special property of the matrix. Okay, and these always exist. This is the top eigenvector. This is the largest eigenvector. Okay, which means that if you run the power method, you're going to get back this eigenvector. Okay. Okay, we went a little bit long, so I'm going to wrap up. I'm going to give you, I'm going to very quickly, give you algorithms for computing Q star, and then we're going to revisit this and talk about Metropolis algorithm, which is a different version of this on Wednesday, and it'll fit in with that lecture. So let me tell you, there are going to be 4 algorithms to computing this, okay, to computing Q star. The first one is what we just talked about, the eigenvector of P. It's going to be the top so eigenvector V1. If I take P and I run my eigenvector calculation, I'm going to get the top eigenvector. We'll have to be a little bit careful. Q star is going to be V1. I have to L1 normalize it, right? So I have to do L1 normalization. V1 will be in S kind of M minus 1, right? So that's going to be L2 normalized. I need to L1 normalize to get the actual Q stars. Okay, but it corresponds with the top eigenvector here. Just a scaling of it. Okay, I can also think about that Qn equals P times P times P times any initial Q for n for steps for n large. Okay, so I can just multiply by the matrix P over and over again. If you've taken foundation of day analysis, you might recognize this as the power method. This is how you would implement probably the power method. Okay, and so this is a linear algebra kind of method for computing the top eigenvector. It also works here. That makes sense. You could also say that Qn for a large enough n is going to be P to the n Q for some initial state for large enough n, right? So I can pre-compute P to some matrix n. I can pre-compute this. This is a matrix, but I'm doing matrix multiplication. Might as well pre-compute P to the n. Okay, in fact, if n equals 2 to the k, then I can compute P squared, then get to P4, then get to P8, then P to the 2 to the k after k steps. So I could maybe even do a logarithmic number of steps to get to some large value. Maybe this is better. Okay, and then the fourth way is I can actually do a random walk on P and keep track of where I walk. Okay, I can walk around the graph and keep track of every time I take a step. Okay, I was in node 7. I take a step. Okay, I was in node 8. Oh, I've been there before, so I have a counter. I keep track of the counter. Okay, and I keep track of counters of everywhere I walk, and I just keep track of this. Okay, and these are 4 different algorithms, right? And we're out of time, and I'll take your question. We'll start Wednesday by talking about when each of these is more efficient. I want you to start thinking about it. Which ones do you think are going to be the most efficient? And then, yeah, well, let's do a quick vote. Who thinks the first one is the best algorithm? Thinks the second one? Thinks the third one? Who thinks the fourth one? Okay, so not. There's advantages to all of them, so no one was completely wrong, but the answer may not be what you expect. It may not be what most of you expect. Okay, great. Question.
How many steps would you do there? Large enough?
Yeah, how big does that need to be? Pretty big. It needs to be larger here for the fourth method than it does for the second and the third. The second and the third are the same, because they're keeping track of distribution. This is much noisier, so you need even more steps. But each step of a constant time could be, or maybe a very fast operation problem, where these are more expensive.